Hey audience, I figured I'd participate in No Effort November and just put no effort at all into a video. So I've got a big pile of chips here, and you notice a couple of these are labeled as broken. I think those are 74 S37s. Hold on, I gotta let this cat in. Hey. Alright, so a couple of these are labeled as broken because they're broken. I used these in a project years ago. Kitty, stop that. I used these in a project years ago, and it took a long time to figure out that these were actually broken. Usually when something goes wrong, it's your own fault, and usually you can trust your parts to be... Kitty, stop bumping that camera. Usually you can trust your parts to be functional. So it's bad enough that you're not expecting the things that you can't control to fail. But then once you start to suspect that some chip or something might be broken, then you have to test it. Kitty, be quiet please, Daddy's working. So here are the inputs, 0, 0, and they all have 1s, like you would expect from NAND gates. And let's try 1, 0. Okay, that looks fine. 0, 1. Well, one of them isn't quite working right. So even with this box of switches and lights, that still was kind of a pain to set up. More of a pain than I would like. I would like something like this, where I can just pop the chip down into a socket, clamp it down, press a few buttons to select what type of chip it is, and then press another button to start a test, and then have it tell me on the little LED screen whether it passed or failed. I don't really care how it failed, because at this point in my life, I'll just throw away bad chips and buy new ones. So it's good enough just to get a pass-fail indicator on the LED screen. So in my last video I talked about problems that I had mixing CMOS and TTL chips on here. And also you'll notice that the chips I want to test are all TTL, and the Arduino is CMOS. So even though it's pretty simple, I'm still going to want to test this on a breadboard before I solder it up on a perf board permanently. But anyway, assuming that it works, what I'm going to want to do is take the digital I/O pins and just connect those right onto the this socket, and I can set those to digital outputs or digital inputs depending on what I need. So I'm going to have to be a bit careful with how I allocate all of these digital pins. First of all, because there aren't very many digital pins to use for testing the chip, at least while leaving me with enough left over for the switches and the LED display. So I'm going to have to get a little bit creative there. I would like to have power and ground both set up at the exact same moment, and at the very least before any of these other pins are set to have any voltages driven to them. So that means that whatever Arduino pin that I use for power and any number of ground pins on the socket, they're going to have to come from the same I/O port. Like here I have port D and then ports B and C. Alright, let's think about how we're going to set up these Arduino I/O pins. So some of these chips get, say, 16 pins. Some of them get 20, 24, even more pins. But for the most part, 16 pins is probably enough. So we want to have up to 16 pins controlled by the Arduino. Port D has 8 whole pins available to us, so let's just kind of put those out here. This isn't how I'll actually lay it out. Let's, because I want the power and ground to be in the same port, but let's go with this for now. D0 through 3, we'll put there. D4 through 7, we'll put there. There's port B, so that gives us 6 pins. So 6 more pins gives us these. And that'll be port B, 0 through 2, and then B, 3 through 5. We have port C, which has another, actually 7 pins, but C6 is also the reset pin. You can use that, but you also lose your reset pin, and it's kind of hard to get it back. So we'll leave that there for now. And we'll assume we just have 6 more pins to work with. It seems like we can use C0 and then C1 for these last 2 pins. The little LED display uses I2C, which is very convenient because it only needs 2 pins, and these pins here happen to be set up for I2C, and that leaves us with 4 pins, which is still, you know, more than the 2 we need, so that's nice. But we need, let's say, like 4 or 5 push buttons. So normally when we connect a switch to an Arduino, we would do it something like this. There you go. The switch just hooked up to one of the Arduino's pins and then connected to ground, and then we'll have the Arduino's input pin at a pull-up resistor. But here, if you want N switches, you need N pins. And that kind of sucks, because I want to have at least 5 switches, which means I'm going to need 5 pins, which is more pins than I have available right now. There are other ways to use fewer pins for more switches. Like, for instance, you could have a matrix of switches like this, where you have one I/O pin per row and then one I/O pin per column. And then the combination of one of the rows and one of the column pins tells you about the status of one of the switches. So now, one pin can give you information about multiple switches because it's taken pairwise with a bunch of other input ports. If you have N rows and M columns, you can have N times M switches with only N plus M pins. But we can do even better than that. While each pin can be taken pairwise with a bunch of other pins, there are other pins that it's not taken pairwise with. For instance, this row pin right here is not taken pairwise with this row pin over here. So that's free real estate, right? You could take that and you could put another switch on it, and then you could have another switch just by taking these 2 pins pairwise. And the same thing with every possible pair of row to row pins and column to column pins. You'll notice that that if we took these 2 pins pairwise, suddenly that would not just tell us about the information about this switch, it would also tell us the information about both of these switches. So if both of these switches are pressed at the same time, it will look like this switch is pressed. But this is no effort November, and we're just going to say don't press more than one button at the same time. So this new, even further improved setup where you're taking every single one of these pins pairwise instead of just rows and columns, that's called Charlieplexing. And then you can also double the number of switches from there, again, by using diodes. Let's say we have 2 switches, but each one is attached to a diode pointed in the opposite direction. Now you can have 2 buttons instead of just one, because you could make this one the pull-up and this one the ground, which would tell you information about this switch, or you could make this one ground, and you could make this one the pull-up, and that would tell you information about this switch here. So I want to have at least 5 switches, and it turns out we can do that with Charlieplexing and with these diodes with just 3 pins. So this does require extra components with these diodes, but the more important thing here is to reduce the number of pins that are required for this. The other option is just to use a microcontroller with more I/O ports. Like this would do just fine. This is going to have more than enough digital I/O pins to handle anything I would throw at that. But I don't really want to use this, because I can't fit it onto a nice little board like that. So we're doing this the hard way, because no effort November. We're doing this the hard way. But we still don't have enough pins. So here we have C0 and C1 going to the socket. C5 and C4 are the I2C clock and data. So we only have 2 pins left for all of our switches, and we need 3 of them. So now is when we get creative. And so the question is, if we have 3 pins for our switches, can we share some of the I2C pins with the push buttons and have it still work? So if we think about how we scan for the switches, we set all of them to inputs with pull-up resistors, and then one at a time we set them to output low, and then we look at the other pins. So while we're scanning for keys, at any given moment only one of these will be outputting low, and the other ones will be held high by the pull-up resistors. But if we look at the I2C protocol, we see that a transaction is started when the data line is pulled low. So if the data line is held high all the time, we should be able to pull the clock line low every once in a while as a treat without actually starting any I2C transactions. So we should be able to connect the switches up to the remaining 2 pins, and then also to the I2C clock. So then whenever I want to scan for the push buttons, I can disable the I2C logic so I can get control of that pin again. And any devices on the I2C bus are just going to ignore the clock line being pulled low because the data line is still being held high. And that gives us the ability to read 6 switches, the ability to control a display over I2C, and only uses 4 I/O pins, which leaves 2 pins from port C available to control 2 pins on the chip that we're testing. So that gives us a full 16 pins that we can play with. Alright, so here we go. I can punch in 37 for testing an S37 chip, and let's go ahead and put in good one, boop, and then test it. That one passed, and then pop that out, and then put in a broken one. Make sure I have pin 1 in the right place. Boop, and boop, and that one failed. And I have the 7404 in a few different flavors. Let's see what this one is. Well, the camera won't focus on that. This is just a plain vanilla 7404. Okay. And this one is a 74HC04. Alright. And this one should be 74HCT04. Alright, seems like the Arduino can drive any logic family that I'll stuff into that. Well, this is a disappointment. So it worked fine for my 74S37. It seemed to work with 3 different flavors of 7404 inverters. But the problem I was really worried about was clock signals, because I was seeing problems with clock signals when I was mixing TTL and CMOS with my switch box. So I wanted to make tests for both the rising and falling edge triggered chip. So I used the 113 and the 109 from my switch bounce detector. But sure enough, the 109 doesn't work. Test fails. So most of the tests actually pass for this for the 109. The asynchronous preset and clear work fine, and the clock signal actually seems to be fine when we're asserting either the J input or the K input, or neither. But when I assert both the J and K input of these JK flip-flops, it won't toggle, which is exactly the behavior that I was seeing when I had this little switch bounce detector hooked up to my switch box. So it looks like I can't use the Arduino to test TTL chips, and that makes me sad, and I'm just going to give up on this project. I did try a few things to see if they helped. I did try some pull-up resistors on the clock pins. I tried some capacitors on the clock pins, but nothing seemed to work. So I really have no idea why this is happening, or why I can't drive a clock signal from a CMOS circuit. But it only seems to happen when I'm trying to toggle this JK flip-flop. So maybe it's something timing related or race condition related. So if it is timing related, maybe some kind of filtering could fix it, but I haven't figured it out yet. If anybody has any ideas, let me know in the comments. But otherwise, I'm just going to give up on building this project. But I'll still put the code up on GitHub, put a link in the description in case anybody wants to see it. It's complete garbage because it's no effort November, but maybe I'll clean it up at some point. But that's it for this horrible failure, and I'll see you next time. Kitty!